Hello, this is Truth Socrates. Welcome to a portrait of linear algebra. This is actually the last video for my Math 10 class at Pasadena City College. So I decided to wear this t-shirt to, well, make this a special occasion. This is from the 1992 Los Angeles Marathon, which I ran. Not very fast, but I did finish. And I was thinking to myself that trying to learn online virtually is very difficult. And it was a lot like running a marathon, actually. So if you just put one foot in front of the other, one foot at a time, you'll make it. So I'm glad that we are here. We are close to the finish line. And it has been a great adventure. Tomorrow is also Thanksgiving Day 2020. So I hope that you celebrate a blessed and safe Thanksgiving. And hopefully years from now, we can put 2020 behind us and life can go on as normal. And we will have all of our loved ones to celebrate with in person again. So with that, today's video is about the orthogonal diagonalization of symmetric matrices. Okay, so I hope you remember the concept of diagonalization. You have a matrix, and if you have a complete set of eigenvectors, in other words, the dimensions of the eigenspaces add up to n, where n is an n by n matrix, then you can diagonalize your matrix. You can put together an n by n matrix with the eigenvectors into columns, and that should be invertible as long as you have a basis for each eigenspace. And what do you get? Something like C inverse AC equals a diagonal matrix B. Okay, so that was in section 8.3. If you need to review that video first, you're welcome to do so, of course. Come back to this one later. Okay, we also saw symmetric matrices first when we talked about projection and reflection matrices. Okay, so we're going to find out today that symmetric matrices can be diagonalized using what is called an orthogonal matrix. Okay, so let's see what we're going to do today. We are going to look at this special family called orthogonal matrices and what makes them special. What are their properties? Then for the main event, we will look at symmetric matrices and we will see that their eigenvalues and their eigenvectors are very special. They're almost what you might call magical. I think they're magical. And we will learn how to orthogonally diagonalize a symmetric matrix. What this means is that the invertible matrix that we create to diagonalize a symmetric matrix can be chosen to be this kind of special matrix called an orthogonal matrix. All right, so what are these orthogonal matrices? An n by n matrix Q is called orthogonal if Q times its transpose is the identity matrix. So that means that Q must be invertible according to the 2-for-1 theorem. And of course, that also means that Q transpose times Q has to be the identity matrix as well. Okay, so Q will be invertible and its inverse must be its transpose. And this is great because usually, how do we find the inverse of a matrix? It's a lot of work, unless of course you have a calculator, right? You have to put the identity beside it, and then you have to get the REF, and after that, the inverse is found on the right side after the identity matrix, which will be on the left side. Okay, so this is awesome. All you have to do is flip the matrix, take the transpose to get its inverse. Okay, well, what should they look like? Let's start with a 2x2 matrix. Here's a generic 2x2. Let's find its transpose. There it is. Okay, so exchange B and C. Okay, we want their product to be the identity. What is their product? That's the product. So we want to satisfy the equation that must now be 1, 0, 0, 1. Okay, well, what does that mean? Of course, a squared plus b squared must be equal to 1. C squared plus d squared must be equal to 1. Where do we see a squared plus b squared? When we take the length of a vector. So that means that AB must be a unit vector. Okay. Oh, wait a minute. There's another one. So AB and CD must be plural unit vectors. Okay, but what else has to happen? There are these zeros. Oh, good, they're the same. We get AC plus BD in both entries here. What is AC plus BD? Okay. You know what? We can think of that as a dot product. Okay. So that equation can be interpreted as AB dotted with CD must be equal to 0. Do you see it? A times C, A times C. B times D, B times D. That's a dot product. Okay. So the first row and the second row, both rows have to be unit vectors, and the two rows have to be orthogonal to each other. Okay. You know what? Let's also look at the other product. How about Q transpose Q? So this time we put this here, Q transpose on the left, Q on the right. Oh, wow. So we get something different. We get A squared plus C squared. Yeah, so that also has to be the identity. Okay, but where is A and C? Oh, now column 1 has to be a unit vector. D and D. Column 2 has to be a unit vector. Okay, and AB plus CD. Yeah, AB plus CD, the dot product of the two columns. Okay, so this sentence is also true for the two columns of a matrix. Okay, so let's make an example, right? Let's make a unit vector on the first row. Okay, so let's make it nice. How about 3/5, 4/5? Okay. And the second row should also be a unit vector, except they have to be perpendicular. Okay, so it can't just be any unit vector. They have to be perpendicular to each other. Okay, so what's one way to do that? Well, how about I put 4/5 here, so that gives us 12 over 25. So to get a minus 12, I need minus 3/5 here. Okay, so do the columns work out? 3/5, 4/5, that's also a unit vector. 4/5 minus 3/5, that's also a unit vector. Are the columns also perpendicular? 12 minus 12. Ooh, looks like it's going to work. Let's try. Compute matrices transpose. Oh, wow. So Maple likes making fractions. Okay, fine. Are you? Yes, you are. That product is the identity. And of course, if you change the order, that is also going to get us the identity. Okay, so let me do this again. We started out with 3/5 and 4/5, right? Was this the only way to fill out the second row? No, not quite. We can have minus 4/5 there. And now we will need positive 3/5 there. Okay, so you can check again. Those are orthogonal columns and orthogonal rows. Transpose, multiply. Yep, that's the identity. Change order. Why am I even bothering? By the 2-for-1 theorem, that should also be right. All right, so we can actually generalize these observations. The following conditions are equivalent for an n by n matrix Q. Q is an orthogonal matrix, meaning Q times Q transpose is the identity. And the columns of Q must form an orthonormal set in Rn with respect to the dot product. Why orthonormal? Well, we wanted the two rows to be orthogonal to each other, and we wanted the columns to be orthogonal to each other. Okay, so that's what 2 and 3 are saying. But also we got a squared plus b squared equals 1, right? And a squared plus c squared equals 1. Okay, so why is this true in general? Okay, so let's think of an n by n matrix as partitioned into, how about columns? Okay, so let's make a matrix. Okay, so I'll make it one. It looks like it's a 1/4 matrix, but here's column 1, column 2, and so on. Let's put that to column n. Okay, that's not a 1/4 matrix. Okay, I am representing an n by n matrix by putting column 1 here, column 2, up to column n. So that's really an n by n matrix. Okay, what does orthogonal mean? Okay, so if this is called Q, what do we want? We want Q times its transpose. I guess I need to borrow the transpose symbol here. We want Q times its transpose to be the identity. Okay, so what are we going to do? Oh, and of course also we want the reverse. We want Q transpose times Q to be the identity. Okay, so if that is the Q, what does Q transpose look like? So this time we're going to write it vertically as a 1/4 matrix. Okay, all right, except here's what's going to happen. We have column 1 over here. When we transpose it, it becomes a row. Okay, so my apologies, I have it backwards. It should be a 4/1 matrix over there. So in row 1, we are going to get column 1 transpose. Okay, so let's see if I can borrow the transpose symbol here. There we go. Okay, and then what happens to column 2? It turns into a row, and that's now column 2 transpose. Keep going until you get column n transpose. Okay, but now, how do you multiply two n by n matrices? Okay, so on the left, remember, partition it into rows, and on the right, partition it into columns. Okay, so which of these are in rows? It looks like it's QT. Okay, so let's make a copy of that. Q transpose is already in rows. Q is already in columns. Okay, so we want that product to be the identity matrix. Okay, but let's think about that. C1 transpose times C1. Oh, wait a minute. That's just C1 dotted with itself. What corresponds to it in the identity? It has to be a 1. Aha. So C1 has to be a unit vector. Okay, how about column 2? Now C1 transpose times column 2 has to be 0. Oh, wait a minute, that means that they're orthogonal to each other. So C1 has to be orthogonal to C2 all the way to Cn. All right. How about C2 transpose? We already know it's C2 is orthogonal to C1. So C2 dotted with or multiplied to C1, that gives you 0. The dot product is 0. C2 transpose times C2. So now we're on row 2, column 2. What does that correspond to in the identity? There's a 1 in row 2, column 2. So C2 dotted with itself has to be 1. C2 has to be a unit vector. Okay? So each of the columns has to be a unit vector, and each column has to be orthogonal to every other column. That's the meaning of an orthonormal set. Okay? And you can play the same game, of course. We can relabel this so that we have row 1, row 2 to row n. Now when you transpose, the row becomes a column. So this becomes row 1 transpose, row 2 transpose, row n transpose. Same game. Row 1 dotted to itself has to be 0, and row 2 dotted to itself, row 1 dotted with itself has to be 1, row 2 dotted with itself has to be 1, and so on. But row 1 dotted with row 2, row 3, and so on. They all have to be 0. All right, so what that means is we can recycle our work from 9.3 once again, just like how we recycled it in 9.4. Remember, these were the 4 output vectors to the Gram Schmidt algorithm. Okay, so these are supposed to be orthogonal vectors to each other, and they are also unit vectors. So I've taken the liberty of putting them into columns. Okay, why do they look different? Well, that's because I computed each of these vectors. Let me show you. Okay, so I put the 1 over square root of 10 inside, and then I took the transpose. Matrices transpose. Okay, so that's what I put into column 4, the last vector. Okay, so repeat for column 1, column 2, and column 3. Okay, so here's column 1, column 2, column 3, and column 4. Okay, so Maple think it's being helpful by simplifying the fraction into lowest form and rationalizing the denominator. Fine. It's still the same vector. Every column is the same as this vector. Okay, compute matrices transpose. Okay, so this is our Q. This is our Q transpose. Okay, what happens when we multiply them together? Yep, we get the identity. Okay, and of course, if we switch the order, transpose on the left, and then matrix on the right, and do we get also the identity? Of course we have. Okay, so now we get to the magical properties of the eigenvalues and the eigenvectors, the symmetric matrix. Okay? If A is a symmetric matrix, then all of the eigenvalues of A are actually real numbers. This doesn't happen all the time. If a matrix is not symmetric, you could have imaginary eigenvalues. Okay? Furthermore, if lambda 1 and lambda 2 are distinct eigenvalues, and v1 and v2 are corresponding eigenvectors, then their dot product is 0. So eigenvectors from distinct eigenspaces are orthogonal to each other. And again, this does not happen in general. The first sentence is very difficult to prove. And it is actually the reason why I wrote chapter 10. It takes an entire chapter to prove this single sentence. Okay? And to do that, you have to look into complex matrices and vector spaces and complex inner product spaces. Okay? So if you're not doing anything over the holidays, why don't you read chapter 10? However, we can prove the second sentence. We will be able to show, not just by example, that two eigenvectors from distinct eigenspaces are always orthogonal to each other. Okay? But let's demonstrate both of them on this matrix. Okay? So remember what a symmetric matrix is. Okay? When you transpose it, you get exactly the same matrix. Okay? That means that that 2 has to be the same as that 2. That minus 4 has to be the same as that minus 4. Okay? And that 2 is also the same as this 2. Okay? So let me be honest with you. This is actually a very special kind of symmetric matrix. Notice that if you look this way, you also have that those 2's and those 2's reflect each other, and the 5's also reflect each other. Okay? It's what's called a bisymmetric matrix. Okay? I should write that down. Maybe you will Google it. So it's actually a bisymmetric matrix. Okay, so let's look at its eigenvalues, right? So let's go compute matrices, characteristic polynomial. Okay, so there it is. What are the eigenvalues? Well, compute, and will it factor it for us? Ooh, excellent. So therefore, the eigenvalues are 0 and 9. But 9 is a double root. Okay, multiplicity 2. I remember that term. Okay. So let's talk about the eigenvectors. Right? So for lambda equals 0, so what's the idea again? From A, we subtract lambda times the identity, but lambda is 0, so it's just A, and we look for the null space. Compute matrices, null space. You know what? RE. Okay, there you go. There's our null space. Okay, and since you saw it, might as well use it. Null space basis. Yeah, okay. So it is a one-dimensional space. All right, we have one free variable. So yeah, if you want to clear the fractions, you'd want 2 minus 1 and 2. Okay. Now, how about the other eigenspace? So that would be lambda equals 9. So you remember what to do. You take the matrix, and from the diagonal, we subtract 9. Is it all coming back to you now? Minus 9, minus 9. Okay? So it should be a minus 9 times I3. Okay? Which means subtract 9 from the diagonals. That's what we get. Ooh. Compute matrices REF. Okay. So this time we have two free variables. Okay. Null space basis. Okay, so let me scroll over here. So it's now two-dimensional, of course. Let's turn them into integers. 1, 2, 0. The other one is already integer. Okay, the theorem says that if you take an eigenvector, one from each eigenspace, they should be perpendicular to each other. Are they? What is the dot product of this eigenvector with each of these? Take the dot product with the first one. What do we get? 2 minus 2 plus 0. Yay! That is equal to 2. Okay, what about the other one? 2 minus 2, 0, dotted with negative 1, 0, 1. We get negative 2 plus 0 plus 2. Yay! That is also 0. We're going to go back to this example later, but I want to give you 2 bonus examples. Okay? I said this is a very special kind of symmetric matrix. Okay? It's bisymmetric. So if I turn this into a 1, I have to turn that into a 1 to keep the symmetry. Okay? So let's ask, oh dear Maple, what is the new characteristic polynomial? Very different. Okay, what was it before? It was this nice polynomial. Very different now. Okay, so it's not, is it factorable? Let's see. Compute, factor, and not quite. All it did was reorder. Okay, so what am I going to do? I'm going to set that equal to 0. Okay. The fact that it's not factorable tells me that the roots are not nice. They're not integers, dream on. They won't be rational numbers either. Okay? Because remember, the integer roots theorem says that the rational roots of this polynomial are actually integers. So if they're not integers, they gotta be irrational. So, compute, solve, numeric. I believe this is the first time we're using this routine. Ooh, ugly. Okay. So notice, oh wait, before it was 0 and 9 was a double root. Okay, look what happened. With this small change, I turned the 2's into 1's. The 3 roots are now distinct, okay, but they're close to 0 and 9. Right? Those are not that far from 9. That's not too far from 0. Okay? And that's because we only changed it by just a little bit. Okay. What's another way to break the bisymmetry? Okay. Let's turn that 5 into a 4. Okay. So now, compute matrices, characteristic polynomial. Again, different. Okay. Any chance that that can be factored? Oh, check it out. 9 is still a root. Okay. But this guy probably has irrational roots. Okay, let's make a copy. Okay. So set that equal to 0. Compute, solve, accept. Okay. Maple can do the quadratic equation very easily. Yep. You have 2 irrational roots. That's basically 4 plus or minus 2 radical 5. Okay. So the theorem, remember what the theorem says. The eigenvalues are always real for every symmetric matrix. Okay. So as long as you have a symmetric matrix, those are still real, those are still real, along with this 9. Okay. Unfortunately, irrational numbers might show up. Okay. Now, I was not planning on a third example. However, let's just try. Okay. What if we broke symmetry entirely? What if I turned that 1 into a 2? That's no longer symmetric, right? So, compute matrices. Okay, again different. Any chance it's factorable? Oh, still factorable. Okay. Is this guaranteed to have real roots? Okay, and this is why I said I wasn't planning on this. Okay, so let's set that equal to 0. Compute, solve, accept. It's still real. Okay, so yeah, just because it's no longer symmetric doesn't mean that you can't have real roots. Okay, but in general, if you do break symmetry, you might have imaginary roots. Okay, let me give you a really cheap example. 2 by 2. 0, 1, 1, 0. That's a symmetric matrix, right? And we can say, okay, compute matrices characteristic polynomial. Yeah, okay. So of course the roots are plus or minus 1. Okay. Speaking of plus or minus 1, what if we turn this into a minus 1? No longer symmetric. Compute matrices characteristic polynomial. Okay. That no longer has real roots. Okay, the roots are plus or minus I. Okay, so as I mentioned, we are able to prove that eigenvectors from different eigenspaces have to be orthogonal to each other. Okay, so to prepare for that, remember what happened when we proved in general that the rows and the columns of an orthogonal matrix have to be perpendicular to each other. Okay, so what happened? We took a column and then we transposed the matrix so the column turned into a row. Okay, and so when we did the matrix product, it felt just like a dot product because we were multiplying the same number to itself. Okay, so that's going to be one of the ideas that we're going to use in this proof. All right. So first of all, let's distinguish between a vector and the corresponding column matrix. Okay. When we were back in section 1.6 and we first defined the matrix product A times X, it means turn the vector X into a column matrix. Okay. And that's what we multiply to A. Okay. So V is the original vector from Rn, written horizontally, and V with brackets around it means the corresponding column matrix. Okay? So what does that mean? If V and W are both from Rn, we can write their dot product, V dot W, in general, as a matrix product. Okay? So we can take W, make a column vector, transpose it. So that's now a row matrix. And then turn V into a column matrix. You're now multiplying a row to a column. Okay? That's exactly what you do for a dot product. You have W1, V1, W2, V2, and so on. That's the dot product. Okay? We didn't cover the section on special families of matrices, where we saw upper and lower triangular matrices and so on. In that section, we see a product rule for the transpose operation. Okay? And if you want to read it, of course, you're welcome to do so. If C and D can be multiplied in that order, then the transpose of C times D must be D transpose C transpose. Okay? So you change the order and then you take the transpose. I hope that reminds you of a similar formula, inverse, right? If you had CD inverse, it's the same as D inverse, C inverse, if both are inverted. Okay, so now we are ready to prove the orthogonality of two vectors from distinct eigenspaces, V1 and V2. We want to show that their dot product is 0. Okay, I was hiding that a little bit. Instead of looking at the dot product directly, we are going to look at something else. We will look at V1 dot AV2. Okay, and you're going to find out in a little bit why that is the right thing to look at. Okay, so we are going to use all this preparatory stuff that we talked about up here. Okay, so maybe I should keep it. Okay, let me keep it like that for now. Okay, so one step at a time. V1 dot AV2. Okay, start with that. Let's change this now. Okay, so I said matrix product. Rewrite it this way. Okay, so let's put parentheses. And then let's put a times there for emphasis. And that's V2. So let me borrow this. And I will turn that into V sub 2. Okay, so AV2. Okay, your AX means 8 times X. So AV2, 8 times V2. So far, so good. Okay. Next step. We're going to use this property. Okay. So what's going to happen? I will put this on the left and then take its transpose. Left, take the transpose. Okay. This one goes on the right times V1, written as a column matrix. So I need a V1 down here. Next ingredient. Transpose of a product. Ooh. Okay. So that formula says on the left we should have V2 transpose. So this is all happening inside the parentheses. V2 transpose. There's an errant times there. But that times should go on the right. Okay, and if you like, yeah, that can go in that formula as well. There you go. If the product C times B. Yeah, that looks a little better. So we also have to take the transpose of A. Okay, so this time we have times A transpose on the right. Okay, and then that product in parentheses multiplied to V1. Gosh, what can we do next? I'm out of tricks. We've spent all of them. But you know something, or you better. You have two products here, pair of parentheses, ring a bell. We have what property? Associativity. That's the one thing I miss about online teaching, making these videos, making you come up with the answer. Okay, so we have A transpose times V1 regrouped. Okay, last step. Equations work both ways. Okay, so we see here a matrix times a column vector. Okay, so we can rewrite this as A transpose times V1. There you go. Okay, so that is where we are. Oh, wait a minute. There's one more step. One more thing we can do. A is symmetric. Okay, so A is symmetric, so therefore A transpose is exactly the same as A. Okay, oh, and I lost something. Wait a minute. How come there's no subscript here? That's because, yeah, that should have a V2 here. And this has V2. And that has V2. That has V2. I don't know where it went. Okay, there you go. That's much better. Actually, I'm still here. Okay, I forgot the last step. There's still one more thing we can do. Right? We have V2 transpose here times AV1, which has the exact same form as this side of this equation. Ooh. And again, equations work both ways. Right? So this equation says that we can turn it to this dot product. Right? So how does this work? The factor on the right goes to the left, and then we have the dot product with the vector on the left, ignoring the transpose. So we take V2 and we put it over there. Okay, now we've done everything that we can. What's the big picture? What do we get? V1 dotted with AV2 must be equal to AV1 dotted with V2. Okay, and I guess we don't need the parenthesis anymore. Okay, the product A times quantity V1 dot V2 does not make sense, because that would be a matrix times scalar. Yeah, that would give you a matrix. On the left you have a scalar. That won't make sense. Okay, so that's the big picture, but now let's not forget that V1 and V2 are eigenvectors. Okay, and the eigenvalues are respectively lambda 1 and lambda 2. So the left side becomes V1 dotted with AV2 becomes lambda 2 V2, scalar product. On the right side, we have AV1 that turns into scalar product lambda 1 V1 dot V2. Okay, but wait a minute. There's another property we can use. It's called homogeneity. Okay, we can take out lambda 2 from the dot product, and we will have V1 dot V2 inside the parentheses. Similarly, on the right, you have take out the lambda 1 from the dot product. You're left with V1 dot V2. Hey, wait a minute. That's the same V1, V2. What is going on here? You have V1, V2 on both sides. What are we supposed to show? It's supposed to be 0. We want to show that the dot product is 0. Okay, is there another way to satisfy that equation? What are we going to do? Oh, wait a minute, before I do that, 2 more steps. Make the right side join the left side. Now the right side is 0. Last step. Factor out V1 dot V2. What's left? Lambda 2 minus lambda 1. So lambda 2 minus lambda 1 multiplied by V1 dot V2 must be 0. Okay? And you know what? I love this section because we're back to day 1. Literally, day 1. First video that you ever saw. Why? These are no numbers. They're just scalars. Okay? Lambda 2, lambda 1, they're scalars. V1 dot V2, that's a scalar. The product is 0. What's that? 0 factors theorem. By the 0 factors theorem, either lambda 2 minus lambda 1 is 0, or V1 dot V2 is 0. So there's one possibility, one other possibility. Oh, but wait a minute. Is this really a possibility? No. Because lambda 2 is different from lambda 1. Okay? So therefore, the dot product has to be 0. Since lambda 2 and lambda 1 are distinct, we must have V1 dot V2 has to be 0. End. Okay, so now we come to our last computation, last topic. We are actually now ready to orthogonally diagonalize a symmetric matrix. And we can do that because we can wrap everything together as the spectral theorem for symmetric matrices. Now we think of spectral, it almost sounds evil, doesn't it? You know, spectrum and all that. But spectrum actually means the set of eigenvalues of a matrix. Okay, so if A is a symmetric n by n matrix, then we can find an orthogonal n by n matrix Q such that Q diagonalizes A. In other words, Q inverse times AQ has to be the same as Q transpose AQ. Why? Because Q is orthogonal. Q inverse is just Q transpose. And when you form that sandwich, you get a diagonal matrix D. And of course, it contains the eigenvalues along the diagonal. And these eigenvalues have to be real numbers. Okay? So why is it that we can do this? Well, what is not so obvious, okay, aside from the eigenvalues being real, what is not so obvious is that the multiplicities of each eigenspace have to add up to the dimension of the matrix. Okay, so we're going to go back to that example that we had before, where we did see that one dimension is one single eigenvector, and the other eigenspace was two-dimensional. All right, so here's that example, and now we get to finish it off. We're going to construct an orthogonal matrix Q, which will diagonalize this matrix. Okay, so earlier we took the 4 output vectors from 9.3 in the Gram Schmidt algorithm, and we made an orthogonal matrix out of the 4 of them. Okay, here we only have a 3 by 3 matrix. Okay, so we already know that this vector is orthogonal to both of these vectors. Okay, it's not a unit vector though, but that's the easy part. What's the length? 4 plus 4, 8 plus 1. Ooh, square root of 9 is 3. Okay, so therefore the unit vector corresponding to this is gonna be, let me just draw an arrow there. We can turn that into a unit vector, 2/3 minus 1/3, 2/3. Okay. Now, these are not unit vectors, but there's a more, what do you call this? A more serious issue. These two vectors are not orthogonal to each other. Look at that. -1 plus 0 plus 0. The dot product is -1, not 0. Okay? So guess what? The Gram Schmidt algorithm comes in. Okay? So what we're going to do is, we're going to apply the Gram Schmidt algorithm to this basis for the second eigenspace. Okay, so remember the input vectors are W1, W2. We only have 2 vectors. Outputs are called V1, V2. Oh, the preliminary output. Okay, and of course V1 is simply W1. This guy over here. What's V2? Oh gosh, do you remember the formula for V2? Oh, it's a good thing it's waiting for us down here. Okay, so we will take W2, which is this one, and subtract this from W2. Okay, so we will take, okay, what happened? W2, okay, and we will subtract the fraction W2 dot V1. Okay, take the dot product, we said it's -1, divided by V1 dotted with itself. So it's 1 plus 4, we're going to get 5. multiplied by v1. Okay, so of course that's 1/5 plus 1/5. Add them together, we get that vector. Okay, so of course we don't like fractions, so let's turn that into -4, +2, whoops, and 5. Okay, there you go. Let's check that this vector is orthogonal to this vector. -4 plus 4 plus 0. You get 0. Okay, excellent. So now, what are we going to do? We can now turn these vectors into unit vectors. Okay, so we will turn the first vector, divide by its length. We said we have a 5 there. Oh, so it's not as pretty as the other vector. We will divide by square root of 5. Square root, where are you? I always lose the square root. There you are. Square root of 5. Okay. And we'll bring the square root of 5 inside. There it is. So again, it rationalizes. How long is this vector? Okay, 16 plus 4, 20, plus 25, 45. Ooh. So that is square root of 45 contains a 9, 3 square root of 5. So we will divide by the quantity, 3 square root of 5. Okay, so that is our second output vector. And they're now both unit vectors. Okay? Let's bring back the first vector we said is there. Okay, so while we're here, let's remind ourselves. The first vector has eigenvalue 0. The other two have eigenvalue 9. Okay? So when we make the sandwich, 0, 9, 9 has to show up. Okay? Alright. Later. We're almost done. So, reminder, first eigenspace was this guy. Okay, so now we're going to assemble the matrix Q. Okay, we will put this in column 1, column 2, column 3. Okay, yes, because 0 is smaller than the 2 9s. Okay, so here we go. We'll put a 3 by 3 matrix to hold our vectors. I'm going to take this, I'm going to paste it into column 1. Yay! Take this, paste this into column 2. And take this, paste it into column 3. Okay, there you go. Now, you might be thinking, can we factor the 3 and the square root of 5? Unfortunately, no, because there's no 3 over here, there's no square root of 5 over here. Okay, so we cannot factor out those denominators. Okay, so while we're at it, let's check orthogonality. Okay, is this really an orthogonal matrix? Compute matrices transpose. Okay. Is the product equal to the identity? Yep. So it is orthogonal. Okay. So what did the spectral theorem say? Let's go back over here. This is the sandwich that we have to make. Q transpose on the left, A is the bologna, the middle, and Q is on the right. Okay? If we expand that out, we should get 099. All right. Q transpose. Okay, so we said this is our transpose. Okay, we put A in the middle. So where is the A? The original matrix is over here. Okay, and our Q, this is the Q on the right. There you go. Okay, so that is our Q transpose A Q. Okay, drum roll, when we expand this out, we should get 0, 9. All right. That's orthogonal diagonalization. That's our last video for Math 10. Oh, look, ugly matrices. I was trying to make a 4x4 example, and it worked out, but it would have taken a lot more time. So as it is, we are close to an hour. So thank you so much. And once again, happy Thanksgiving. I am very thankful to have all of you as my students. I always tell my friends, my students, I have the best job in the world. So thank you. Thank you very much.